Torchreal. Description: explain in detail. Torchreal is a library that provides methods for real-time inference of PTorch models. It allows you to deploy your trained models on various hardware platforms, including CPUs, GPUs, and specialized hardware like TPUs, and make predictions with minimal latency. Inputs. Input 1: explain in detail model, a PTorch model that has been trained and saved. Input 2: explain in detail data, the input data for inference. This can be raw data, such as images, text, or audio, or pre-processed data that has been transformed into the appropriate format for the model. Outputs. Output 1: explain in detail predictions, the output of the model's inference, which can include classifications, object detection results, or other types of predictions depending on the task. Output 2: explain in detail runtime information, metrics like inference time, resource utilization, and other relevant performance data. Steps. Step 1: explain in detail load the model, load the trained PTorch model from a saved file. Step 2: explain in detail prepare the input data, preprocess and transform the input data to the appropriate format for the model. Step 3: explain in detail perform inference, run the model on the input data to obtain the predictions. Step 4: explain in detail post-process the output, format the model's output into a user-friendly format or perform any necessary post-processing steps. Metrics. Metric 1: explain in detail inference latency, the time taken to perform a single inference on the model. Metric 2: explain in detail throughput, the number of inferences that can be performed per second. Metric 3: explain in detail resource utilization, the amount of CPU, GPU, or memory resources consumed by the inference process. Visualization plots. Visualization plot 1: explain in detail inference time distribution, a histogram showing the distribution of inference times across multiple runs. Visualization plot 2: explain in detail resource utilization plot, a graph showing the CPU, GPU, or memory usage over time during inference. Fine-tune parameters. Parameter 1: explain in detail batch size, the number of data samples to process simultaneously during inference. This can affect performance and resource usage. Parameter 2: explain in detail input data resolution, the size of the input data, which can influence processing time and model accuracy. Uncertainty methods. Uncertainty method 1: explain in detail ensemble methods, using multiple models to obtain predictions and combining them to estimate uncertainty. Uncertainty method 2: explain in detail Bayesian inference, using Bayesian methods to estimate the posterior distribution of model parameters and derive uncertainty estimates. Challenges and fixes. Challenge 1: explain in detail latency issues. High inference latency can make real-time applications unusable. Sample use case that resulted in challenge 1: a real-time object detection system with high latency might not be able to track objects accurately or react in a timely manner. Fixes to challenge 1: optimize model architecture, use faster hardware, or reduce input data resolution. Challenge 2: explain in detail resource constraints, limited memory or processing power can hinder inference performance. Sample use case that resulted in challenge 2: a mobile application with limited resources might struggle to run complex models in real time. Fixes to challenge 2: use a smaller or more efficient model, optimize model architecture, or reduce the input data size. Challenge 3: explain in detail handling real-time data. Real-time data streams can be challenging to handle. requiring efficient data buffering and processing. Sample use case that resulted in challenge 3. A real-time video processing application needs to handle continuous data flow without introducing significant latency. Fixes to challenge 3 use efficient data buffering mechanisms, parallelize processing steps, or implement asynchronous data handling. Torch is tensor. Description. The torch is tensor function checks if the input object is a p-torch tensor. Inputs. Input 1 object. This is the object you want to check if it is a p-torch tensor. It can be any Python object, including lists, tuples, numpy arrays, and other p-torch tensors. Outputs. Output 1 boolean returns true if the input object is a p-torch tensor. False otherwise. Steps. Step 1, the function examines the input object's type. Step 2, it returns true if the object's type is a p-torch tensor. False otherwise. Challenges and fixes. Challenge 1, using a non-tensor object. Sample use case that resulted in challenge 1, passing a Python list or a numpy array as input. Fixes to challenge 1. Ensure that the input object is a p-torch tensor by converting it using torch tensor. Challenge 2, using a tensor from a different p-torch version. Sample use case that resulted in challenge 2, a tensor created using an older version of p-torch. Fixes to challenge 2. Upgrade p-torch to the latest version to ensure compatibility. If the older version is needed, explicitly check the tensor's type using isInstance object. Torch tensor. Torch is storage. Description. The torch is storage function checks if an object is a p-torch storage object. Storage objects are low-level memory buffers that hold the underlying data of tensors. This function is useful for verifying if an object is a storage object before attempting operations that require a storage object. Inputs. Obj, the object to be checked. Outputs. Bool, a Boolean value indicating whether the object is a p-torch storage object. True if the object is a storage object. False otherwise. Steps. The torch is storage function takes a single argument, obj, which is the object to be checked. The function examines the object's type and checks if it's a subclass of torch storage. If the object is a storage object, the function returns true. Otherwise, it returns false. Challenges and fixes. Challenge 1, misunderstanding the purpose of torch is storage. Sample use case that resulted in challenge 1, attempting to use the function to check if a tensor is a storage object. Fixes to challenge 1, remember that torch is storage is specifically designed to check if an object is a storage object, not a tensor. Challenge 2, using the function with an object that is not a p-torch object. Sample use case that resulted in challenge 2, passing a Python list or dictionary to the function. Fixes to challenge 2, ensure that the object passed to the function is a p-torch object, such as a tensor or a storage object. YAML. Torch is complex. Description. This function checks if a tensor contains complex numbers. Inputs. Input a tensor of any shape and data type. Outputs. Output a Boolean value indicating whether the tensor contains complex numbers. Steps. The function examines the data type of the input tensor. If the data type is complex, the function returns true. If the data type is not complex, the function returns false. Challenges and fixes. Challenge 1, the function does not handle cases where the input tensor is a tuple or list of tensors. Sample use case that resulted in challenge 1. Python. Input tensor torch. Tensor 1, 2, 3. Torch tensor 4, 5, 6. Torch is complex input tensor. Fixes to challenge 1. The function should be modified to handle tuple or list inputs by iterating through each element and checking if it is a complex tensor. Challenge 2. The function does not handle cases where the input tensor is a scalar. Sample use case that resulted in challenge 2. Python. Input tensor 1.02.0j. Torch is complex input tensor. Fixes to challenge 2. The function should be modified to handle scalar inputs by checking the data type of the scalar. Torch is conj. Description. The torch is conj input function checks whether the input tensor is the conjugate of another tensor. This function is used for complex tensors, which have a real and imaginary part. The conjugate of a complex number is obtained by changing the sign of its imaginary part. Inputs. Input a tensor of complex numbers. Outputs. Output a tensor of booleans, where true indicates that the corresponding element in the input tensor is the conjugate of another element in the tensor. Steps. The function compares each element in the input tensor with all other elements in the tensor. If an element is the conjugate of another element, the corresponding value in the output tensor is set to true. If an element is not the conjugate of any other element, the corresponding value in the output tensor is set to false. Challenges and fixes. Challenge 1. If the input tensor is not complex, the function will raise a type error. Sample use case that resulted in challenge 1. Python. Input tensor torch. Tensor 1, 2, 3. Torch is conj input tensor. Fixes to challenge 1. Convert the input tensor to a complex tensor. Challenge 2. If the input tensor contains any non-values, the function may return incorrect results. Sample use case that resulted in challenge 2. Python. Input tensor torch. Tensor 1 2j. Floatnan. 3 4j. Torch is conj input tensor. Fixes to challenge 2. Remove non-values from the input tensor before calling the function. Torch is floating point. Description. This function checks if the given input tensor is a floating point tensor. It determines if the tensor's data type is a floating point type like float32 or float64. Inputs. Input 1 tensor, the input tensor whose data type is being checked. Outputs. Output 1 bool true if the tensor's data type is a floating point type. Otherwise false. Steps. Step 1. The function examines the data type of the input tensor. Step 2. If the data type is a floating point type like float32 or float64, it returns true. Otherwise, it returns false. Challenges and fixes. Challenge 1. Incorrect input type. Sample use case that resulted in challenge 1 providing an input that is not a tensor, such as a string or an integer. Fixes to challenge 1. Ensure the input is a valid p-torch tensor. Challenge 2. Unexpected data type. Sample use case that resulted in challenge 2. The input tensor's data type is not recognized as a floating point type by the function. Fixes to challenge 2. Verify that the data type of the input tensor is correctly defined and recognized by p-torch as a floating point type. Torch is non-zero. Description. Inputs. Input a p-torch tensor of any supported data type. Output a p-torch tensor of the same shape as the input tensor. Each element in the output tensor will be a Boolean value indicating whether the corresponding element in the input tensor is non-zero. Steps. Step 1. The function iterates over each element in the input tensor. Step 2. For each element, it checks if the element is not equal to 0. Step 3. If the element is not equal to 0, the corresponding element in the output tensor is set to true. Otherwise, it is set to false. Challenge 1. The function does not handle non not a number values. Sample use case that resulted in challenge 1. If the input tensor contains non values, the function will return true for those elements. Fixes to challenge 1. Implement the check for non values and handle them accordingly. For example, you could set the output element to false if the input element is non. Challenge 2. The function does not handle complex numbers. Sample use case that resulted in challenge 2. If the input tensor contains complex numbers, the function will only check the real part of the number. Fixes to challenge 2. Implement the check for complex numbers and handle them accordingly. For example, you could check the absolute value of the complex number and set the output element to true if the absolute value is not equal to 0. Torch set default D-type. Description: the torch set default D-type function sets the default data type for newly created tensors in PTorch. This setting applies to tensors created directly using torch, tensor, torch, ones, torch, zeros, etc. and also to tensors created within torch, NN, modules where no specific data type is specified. Inputs: D-type a torch, D-type object specifying the desired default data type. Common options include torch, float32 default, torch, float64, torch.int32, torch.int64, and torch, bool. Outputs: none. This function does not return any value. It directly modifies the global default data type setting within PTorch. Steps: set the desired default data type using the torch set default D-type function. The specified data type becomes the default for all subsequently created tensors, unless a specific data type is explicitly provided. Challenges and fixes. Challenge 1. Unexpected behavior when mixing different data types. Sample use case: you might encounter issues if you try to perform operations on tensors with different data types without explicit casting, especially when using functions or modules that rely on the default data type. Fixes: always be mindful of the default data type and explicitly cast tensors to the required data type. Using tensor, type desired type or tensor, to desired type when necessary to avoid potential type errors or unexpected results. Use the torch, promote types function to determine the appropriate data type for mixed type operations based on the default data type and the types of involved tensors. Challenge 2. Confusion about the default data type for specific operations or modules. Sample use case: you might assume that all tensors created within a certain module use the default data type, while in reality, the module might have its own default data type settings or specific data type requirements for its operations. Fixes: always check the documentation for the specific module or operation to determine its default data type behavior and any potential data type requirements. If needed, explicitly specify the data type for tensors used within the module or operation using torch, tensor data, D-type desired type or module input, D-type desired type. Challenge 3. Modifying the default data type mid-execution. Sample use case: changing the default data type during execution can lead to inconsistent behavior if you are not careful about which tensors are being affected. Fixes: try to avoid changing the default data type unless it's absolutely necessary. If you need to change the default data type, do so at the beginning of your script or before the code that will be affected by the new setting. Carefully track the tensors that are created after the default data type is changed to ensure they are handled correctly. Challenge 4. Forgetting to reset the default data type to its original value. Sample use case. You might change the default data type for a specific part of your code, but forget to reset it back to the original value, leading to unintended consequences later in the execution. Fixes. Always remember to reset the default data type to its original value after modifying it using torch. Set default dtype original dtype to maintain consistent behavior across your code. Use the torch get default dtype function to retrieve the current default data type if you need to revert to the original setting. Challenge 5. Data type issues when loading or saving models or data. Sample use case. If you load or save models or data that were created with a different default data type, you might encounter issues when using them with a different default data type setting. Fixes. Specify the data type explicitly when loading or saving models or data to ensure consistency. Consider using a data type agnostic approach for saving and loading data to avoid data type related issues. Check the documentation for the specific libraries or modules used for saving and loading data for any recommended best practices related to data type handling. Torch get default dtype. Description. The torch get default dtype function returns the default data type used by ptorch for new tensors. This default data type is set by the torch set default dtype function. Inputs. None. Outputs. Default data type. The default data type currently used by ptorch for new tensors. This can be either torch float 32 or torch float 64. Steps. Check the current value of the torch set default dtype setting. Return the corresponding data type based on the setting. Challenges and fixes. Challenge 1. Unexpected data type. Sample use case. You expect the default data type to be torch float 64, but it's actually torch float 32. Fixes. Use torch set default dtype torch float 64 to explicitly set the desired default data type. Challenge 2. Inconsistent data types. Sample use case. You are working with a mix of tensors with different data types and get unexpected results due to implicit type conversions. Fixes. Use torch get default dtype to check the default data type and ensure that all tensors being used have the same data type. If necessary, use torch toad type to explicitly convert tensors to the desired data type. Torch dtype. Description. A torch dtype object represents the data type of a tensor in ptorch. It defines the way numerical data is stored and manipulated within a tensor. Inputs. None. Outputs. A torch dtype object that specifies the data type of a tensor. Steps. ptorch provides various torch dtype objects representing different data types, such as torch float 32 single precision floating point numbers. This is the default data type for most operations. Torch float 64 double precision floating point numbers. This offers higher precision but is generally slower. Torch.int 64 64-bit integers. Torch.int 32 32-bit integers. Torch Boolean values true or false. You can specify the data type of a tensor using the dtype argument in tensor creation functions. Torch tensor data dtype torch float 32. You can retrieve the data type of an existing tensor using the dtype attribute. Tensor dtype. Challenges and fixes. Challenge 1. Choosing the appropriate torch D-type for your data. Sample use case that resulted in challenge 1 using torch, float 32 for data requiring higher precision, leading to loss of accuracy. Fixes to challenge 1. Use torch, float 64 for data requiring higher precision. For integer data, choose the appropriate bit size based on the range of values. Challenge 2. Converting tensors between different torch, D types. Sample use case that resulted in challenge 2 trying to perform operations on tensors with incompatible data types. Fixes to challenge 2. Use tensor, type torch, float 32 or tensor to torch, float 32 to convert the tensor to torch, float 32. Use similar methods for other data types. Challenge 3. Using torch, D types in CUDA operations. Sample use case that resulted in challenge 3 encountering errors related to data type compatibility when using CUDA. Fixes to challenge 3. Ensure that the torch, D type is supported by the CUDA device. If necessary, convert tensors to a supported data type before transferring them to CUDA. Torch, set default device. Description. Sets the default device for p-torch tensors. This means that any new tensor created will be allocated on this device by default. Inputs. Device a string representing the desired device. This can be CPU, CUDA, or a specific CUDA device like CUDA 0. Outputs. None. This function does not return any value. It modifies the default device for future tensor creation. Steps. The function takes a device string as input. It sets the default device for p-torch tensors to the specified device. Challenges and fixes. Challenge 1. Attempting to set a device that is not available. Sample use case calling torch, set default device CUDA 1 on a system with only one GPU. Fixes. Ensure that the specified device exists before calling set default device. Check the number of available GPUs using torch, CUDA, device count. Challenge 2. Incorrect device specification. Sample use case setting the device to CPU 0. Fixes. The correct device specification for CPU is simply CPU. Ensure correct syntax for CUDA devices, like CUDA 0 for the first available GPU. YAML. Torch, get default device. Description. This function returns the default device that p-torch uses for computations. Inputs. None. This function does not take any inputs. Outputs. Device a string representing the default device used for computations. This can be CPU or CUDA if a CUDA-enabled GPU is available. Steps. Check if a CUDA-enabled GPU is available. If yes, the default device will be set to CUDA. If no GPU is available, the default device will be set to CPU. Challenges and fixes. Challenge 1. The device returned by getDefaultDevice might not be the device where you want to perform your computations. Sample use case that resulted in challenge 1. You might have a CUDA-enabled GPU available, but you want to perform computations on the CPU. Fixes. Manually specify the device for your tensors and operations. You can use the to method to move tensors to a specific device. Use the torch device object to explicitly specify the device you want to use. Challenge 2. If you have multiple GPUs, the default device might not be the one you want to use. Sample use case that resulted in challenge 2. You have 2 GPUs, but you want to use the second GPU for your computations. Fixes. Use the torch CUDA set device function to set the desired GPU as the default device. Manually specify the desired GPU for your tensors and operations using the torch device object. Torch set default tensor type. Description: the torch set default tensor type function allows you to specify the default tensor type for all newly created tensors. This is useful for situations where you need to consistently work with a particular tensor type. For instance, when you need all tensors to be on a specific device or have a specific data type. Inputs: tensor type a torch D-type object specifying the desired default tensor type. This can be any valid ptorch data type, such as torch, float32, torch.int64, torch, CUDA, float tensor, etc. Outputs: none. This function does not return any value. It simply sets the default tensor type. Steps: the function takes a torch D-type object as input and sets it as the new default tensor type. Any subsequent calls to tensor creation functions, e.g., torch, tensor, torch, ones, torch, zeros, etc., will now use the specified tensor type by default. Challenges and fixes. Challenge 1: forgetting to set the default tensor type back to its original value after using it. For a specific task, sample use case that resulted in challenge 1, you might use torch set default tensor type torch float16 to save memory during training, but forget to change it back to torch float32 before inference. This can lead to unexpected behavior or errors. Fixes to challenge 1: always make sure to revert the default tensor type to its original value. Typically torch float32 after using a custom default type for a specific task. Use torch set default tensor type torch float32 to reset the default to the original type. Challenge 2: using torch set default tensor type with a data type that is not compatible with the current device or computation. Sample use case that resulted in challenge 2: you try to set the default tensor type to torch, CUDA, float tensor when the device is set to CPU. This will lead to errors. Fixes to challenge 2: ensure that the specified data type is compatible with the current device in computational environment. For example, if the device is CPU, use torch float32 or torch.int64. If the device is GPU, use torch, CUDA, float tensor or torch, CUDA, int tensor.